So these energy conservation and region questions seem to keep coming up. So they must be of some importance. And if you like quantum mechanics, then this question in particular is probably in your bubble of interest because it deals with tunneling. So the statement is a charged particle traveling in from negative infinity along the x-axis encounters a rectangular potential barrier of u of x is equal to u naught, and then for 0 to L, and then 0 elsewise. Show that because of the radiation reaction, it is possible for the particle to tunnel through the barrier. That is, even if the incident kinetic energy is less than mu naught, the particle can still pass through. Well, with the pre-acceleration, that kind of makes sense. All right, so in the solution, what we have to do is reformulate our task, which is to solve the equation A equal tau A dot plus F over M. But here we have to reformulate the F as a mu naught over M subject to two Dirac deltas, one at X and one at X, then one at L. Okay, so that's how we formulate them accordingly. So this new equation has to be subject to boundary conditions. So the first one being that X has to be continuous at X equals 0 and L. 2, the velocity has to be continuous at X equals 0 and L. So the Dirichlet and Neumann conditions, again, remember those from the electric and magnetic fields. Here we have delta A, which based on last question, we showed that we could have a Dirac delta in there, but instead of A being continuous, we have delta A on either side of that barrier is equal to plus or minus whatever that external force was, or whatever the constant was on the Dirac delta. So here we have u naught over m tau v plus for x equals 0 and minus for x equals L, because we have to jump up to the height of the potential barrier at 0, and we're leaving the potential barrier at L. So that's why we have plus or minus as such. Therefore, the third of these follows from integrating the equation of motion. So let's go ahead and do that. Again, we've seen the calculus of how to set this up. No biggie. Take the integral with respect to time, shove it through. We get dv is equal to tau dA, or delta A, and then we have two Dirac deltas there that we need to take into account. But we see that dt needs to be kicked out to the curb and replaced with dx, since the Dirac deltas are with respect to dx. So do a little substitution and realize that we have dt over dx, which is actually 1 over v. Okay, and again, since velocity has to be continuous, that second line has to equal 0, since delta v is v2 equal to v1, and they cancel out to 0. So in the third line, we show that that dA is equal to negative mu naught over m tau, and we substitute the fact that we got rid of the dt element with the dx element via bringing over the 1 over v. And now we can evaluate these integrals as such. So with that, we get a mu naught or u naught over m tau v, but that plus or minus that we defined last time, because we have a minus minus for the x equals 0, and we have a minus plus for the x equal L. So good there. Just be aware. You have two signs. Again, it's just because we're lazy and we don't want to write it out again. In each of the three regions, the force is 0. It acts only at x equals 0 and x equal L. Again, that's the start of the barrier and the end of the barrier. And the general solution is A of t is equal to A e to the t over tau. V of t is equal to A tau e to the tau t over tau plus b, just because we have another integration constant. And we integrate that again, so we get another constant there for position. Okay? That doesn't confuse us, I don't think. So what we need to now do is examine everything in region 3, or x greater than L. And so if we want to avoid runaway, we have to pick A3 equal to 0, because we don't want the acceleration to keep going after we exit the barrier. So we use subscripts here just to keep the regions confinement together. So A3 is for the acceleration, B is for the velocity, and C is for the position. But again, we're just doing this in terms of the subscripts just mean that they belong to region 3. So to avoid that runaway, we let the A3 equal 0. So A of t equals 0. We like that. Cool. That's our condition that we impose. If that's the case, the general solution gives us V of t equal B3, and then X of t is equal to B3, t plus C3. Good to go. So if we let the final velocity be VF, then B3 has to equal VF. Okay, so set the clock so that t equals 0 when the particle is at x equals 0, and let big T be the time at which it takes to traverse the barrier, so that what we have here is x of t, because that's when it traversed the barrier, is equal to the total length L. Okay, and the reason why we do this is because now that x of little t term can be modified, and we see that we have VF times big T plus C3, again, still in region 3, so outside the barrier. And so with that, we show that C3 is actually equal to a discrete segment of L minus VF times T. Okay, so now we have all the coefficients for this region, and we show that for T less than big T, these are the equations. Or is it greater? I don't remember. Yeah, we'll just have to be careful of that because the other side goes to 0. So then for region 2, we have x between 0 to L. So our boundary conditions, number 3 gives us dA is equal to negative negative U naught of m tau VF. So what we have is A3 at big T minus A2 at big T is equal to 0 minus AT e to the big T tau. Again, we had we had A3 equals 0 because we set the constant to 0 to get rid of the runaway region. And so, cancel away. We said that's delta A, so we need to put the minus at U naught over m tau VF. So we see that A2 is equal to U naught over m tau VF e to the negative big T over tau. All right, fair enough. Equation 2, continuity equation, or the continuity equation at L. We have that VF is equal to A2, tau e to the negative T, or big T over tau, not negative, plus B2. Again, we saw what A2 was. Now we need to solve this thing for BT. And so we see that the exponentials actually go away, actually tidy up, and we get a factor of tau canceling down. Again, if we have that the final velocity is as such, now we can go ahead and minus it over and solve for B2. Cool enough. We like that. And now, similar method, we just have to apply for L. The position has to equal all of those things at that boundary. So tidy up, but be careful. It does not get nicer. So this is the ugliest of the regions that we have, and that's for T between 0 and big T. So have fun, simplify accordingly. It's not too bad, but it's clearly messy. And we just have to be careful, as always, with the bookkeeping. So what is interesting is how the final velocity is related to the time spent traversing the barrier. In particular, for t equals 0 when x equals 0, we have L is equal to VF big T minus U naught over MVF bracket tau e to the negative T over tau plus T minus tau. The words, I have no clue what I was typing. I must have just gotten excited in my head. But what is interesting is that the final velocity should be the only thing that's there. All right, so for region 1, where x is less than 0, let VI be the incident velocity at t equal negative infinity. Then we can apply the continuities and kind of make things nice. And if we plug in negative infinity to the general form, we see that we get BI equal VI. And then condition 3 allows us to have a plus sign there. So we get 0 minus 0, gives us that plus. We like that. Tidy through, again, nothing new. You've seen these type of equations before, or how to deal with boundary conditions. So where V0 is the speed of the particle as it passes x equals 0. From the solution in region 2, it follows that from 2 and V0, we have Vf is equal to, or V0 is equal to Vf plus U0 over mVf, bracket e to the negative t, big T over tau minus 1. But we can also express it in terms of the solution in region 1, where we have V0 is equal to A1 tau plus Vi. Okay? So therefore, if we solve the region 1 solution for Vi, we get V0 minus A1 tau, but we also know what A1 is. So what V0 is, so we plug that in terms of Vf. And now we can solve a way for what we expect to happen and kind of condense things through. Again, be careful because none of this stuff is exactly pretty, so to speak. So with that, A1 gets substituted in from what we found right above it. And in the next slide, we just tidy up everything, distribute, cancel, factor, all that stuff. So here, with that being said, in the second line after we cancel and factor, what we see with that Vf and V0 term is that if we substitute in V0 again, we get a horrific looking fraction. Everything in that fraction has a Vf in it, so if we cancel out or factor it out, rather, then we get a U0 over mVf squared, okay? And that's exactly what we were trying to show with the Vi, or the incident velocity, can actually show that we have a final velocity on the other side. And yeah, pretty cool. Again, quantum mechanics will have more coursework on this, so I'm not going to spend too much more time on it. But for the sake of energy, if 1/2 mVf squared is equal to 1/2 U0, then U0 is equal to mVf squared, and we see that L is equal to Vf big T minus mVf squared over mVf. We get some cancellations there. We like that. Tidy up the brackets as what we can. And so we see that L is actually equal to Vf tau, bracket 1 minus e to the negative t over tau. Vi, with the same information, gets reduced down. We see we have cancellation of mass and velocity final terms again in both the common factor and in that denominator. So, we cancel it all the way down, and we show that Vi is equal to Vf e to the big T over tau. Okay, so, let that all condense down. Be very careful with your bookkeeping. Here then, putting this all together, we have L is equal to Vf tau, 1 minus e to the negative t over tau. And then solving this for L over Vf tau gives us this exponential that we want. Again, we're solving for the exponential so that we can plug in what we found in the line before it with Vi. And so here, Vi is equal to Vf e to the big T over tau. So if we plug into e to the tau over t in terms of L, now we can have everything we need, and showing that Vi is also related to the length traveled. Okay, so we proved both cases there. And in particular, if we let L equal Vf tau over 4, then Vi reduces down to 4/3 Vf, and we can now find the ratio of kinetic energies. So we have 1/2 m's that cancel, and we just have a ratio of Vi to Vf. But that's cool because that ratio, based on the Vi right above it, goes to 4/3. And if we square that, we get 16/9. So what this tells us is that the kinetic energy initial is equal to 16/9, the kinetic energy final. So, if that's the case, we have 1/2 U0. So we can be up to 8/9 the potential energy, or the energy needed for the barrier, and still get through it. That's freaking crazy.